Okay, hello. So it's 8 p.m. in Japan, so let me get started with this week's Houdini's tutorial live. Okay, today's topic is gonna be really simple to create a Koch Snowflake, which is one of the most famous fractal pattern, I think, in 2D. And it's also one of the easiest ones to implement. So I think hopefully the one that I'm gonna show today will take short time than the other one that I'm always do. And the final outlook of the geometry will be looking like this. So I have a Koch Snowflake as a section of the vase and use it to create something like a kind of a lamp vase, which I saw in one of the images in Pinterest. So I can change the side of the basic curve, number of layers, which is the resolutions, the minimum scale of the vase, and the waviness of the vase, and the angle, rotation angle, and the height, something like that. So more of a basic parametric modeling tutorial it's gonna be. Today's gonna be more of a basic one, hopefully. Right. And the inspiration came from the final shapes. Inspiration came from this 3D printed fractal vase, which looks exactly as what I'm going to create. And this is the actual physical object, so I thought it looks really cool, so I wanted to create something like this. Okay, so let's do this. Hello, thank you for the comment, and let me get started. Right, and the file of today's topic can also be downloaded from the video description I've uploaded just 15 minutes ago. So if you're interested, you can download that to check that out. Right. Now, first of all, let's create from geometry, and let's start by creating a basic curve. So let's go back to the Wikipedia for the definition of the Koch Snowflake. Especially if you look at this animation, GIF animation, it will be more understandable, I think. So it starts with a simple triangle curve, and then each edge of the triangle will have one triangle mountain added on the middle. Then that operation will be continued for each newly created edges of the curve for each curve. So you just need to have one simple operation, just convert one line into a line with small triangles came out of this line on the middle, 1/3 of the size. So that sounds easy. Let's start by creating a base triangle curve by using a polygon, then set it to XZ plane. Then for initial side of the number of the sides of the polygon, let's set it to 3, but I think it also works with any number of sides, so I guess I could also parameterize this division for the circle. So let's create a node controller to have all the parameters that you want to control. name this as you want. Let's have an integer parameter for this one. Let's say size, and start from 3 to maybe around 10. And I'll just go with 3 for initial testing, right? Okay, now what I want to do here is to convert each edge of this primitive into a first Koch Snowflake shape. So I want to convert this edge into a one-third of the size of the edge from the left side, then have a triangle also have the 1/3 of the size of the edge for the mountain, triangle mountain, then have the right side edge connecting to the right edge, right side of the point. So to do that, I am just going to do it by using a primitive Rangel. I guess you could also do it in just using a node, but I think using a Rangel might be a simple way to achieve this. And it's going to be a good practice to learn Vex as well, I think, because it's going to be really simple, I think. So let's do this in this way. So first of all, I am going to use a primitive Rangel, and first thing I would like to do is to get all the points from this primitive. So I'm going to get the number of points using prim points function. Okay, and I'm going to create a empty primitive, which is going to be the next primitive of the fractal shape made it from this triangle, from these 3 edges. So going to add prim as a polygon. Okay, now if you have 3 sides, the number of points will also be 3, so you can imagine that the initial number of operations you have to do for this triangle is 3. It means you just need to loop through the number of points, which is equivalent to the number of sides, right? And in order to get the size, you need to have the point 1 and point 2 for each loop. So for the point 1, it will be the first point from this PTS array, and the point 2 will be the next point from this PT1. So PTS I plus 1, and this I plus 1 could be like number 3, which is more than the number of points. So in that case, you want to reset this number to 0 by calculating the modulus. So something like this, right? And let's also get the position for each point, point 1 and point 2, like this, in order to calculate the 1/3 of the position from the left side and the right side. So position 2.0 ppt2. Okay, right, and now I want to calculate the position of the one that's on the 1/3 of the position from the left side. So it's around here, and also a 2/3 of this edge's length, which is around this point. So let's get that information as well. I'm gonna name the first one to be npos1, and that is starting from the position 1 and subdividing position 2 minus position 1 makes this angle, this vector goes from position 1 to position 2 divided by 3. So as a result, you'll get a point which is on 1/3 of this edge's length around here. Okay, so this is in position 1. Now for the end position 2, same as the end position 1, you just need to do the same thing and finally multiply by 2, and you have the 2/3 of the size of this edge from calculating from the left side. So it's gonna be around here. All right. Okay, finally what you wanna have is the point which is around here makes this small triangle which lies on this edge, which should be the 1/3 of the size of this original triangle. So in order to calculate that, what I'm going to do is to let's say rotate one of the n+1 or n+2 based on the axis on the other edge, other point. So if you're rotating this n+1, then use this n+2 as a rotation axis and rotate it 60 degrees right or left to bring the point up here. So let's try to do that first. So in order to do that, I am going to first create a rotation matrix. So start from the ident, then use the rotate function to rotate the matrix with the radians 60 degrees, minus 60 degrees for now, just testing out. Okay, so the n+3, which is the point that I want to create it around here, is equal to, so let's start from the n+1, which is around here, and add position 2 minus position 1 divided by 3. So this is the vector which goes from the left side and goes to until around the 1/3 of the size of this edge. So this is the vector, right? And I want to rotate this vector by this rotation matrix that I have created here. So multiply by matrix, and as a result I should be able to get the position somewhere around here. Or if the rotation unit is wrong, then the point comes here. So let's check that out later on. Right, so let's check those points out, the new position that I have created, n+1, n+2, and n+3, by using an add point to each of the position. So add point n+1 int npt2 add point n+2 int npt3 add point n+3. Okay, let's check that and let's visualize the points, and I think it seems like the point position is correct for all the edges. So for these edges you have this n+1, n+2, and n+3 point here, which creates this base triangle that I need to have. And same for the other edges, having the same information here. Okay, let me right? Okay, so that looks good. Now, next thing I would like to do is to create a one continuous polygon connecting all those points to make a kind of a star shape. Right. To do that, I already have this empty primitive here, so what I just need to do is to add a vertex into this empty polygon. So to do that, I just need to call the function called add vertex, and to the primitive that I have created, empty primitive that I've created, I'm going to add the point I want to use it to create this star shape. So the first point will be this PT1, I guess. PT1. And the next point will be an PT1, which is this one. Next point will be an PT3, which is this point. Right, add vertex, and next one will be MPT2, which is this one. And I think I can stop it right here. I don't need to add this one because I'm looping through all the edges here. And so if I finish 1, 2, 3, 4, then in the next loop I start from this point. So I don't need to add to this point because that point will be duplicated in the next loop if you add the endpoint, which is this one. So you can ignore the PT2 for this. So let's check that out, and yeah, I think it looks good. Now, the one that I have used as a base, which is the triangle shape, could be removed at this point. So let's delete that using remove prim, and like this. Oops. Remove prim. Okay, something looks wrong. Invaried. Remove. Okay, I needed the comma. Right. Okay. Now I have only one primitive here with one iteration of this fractal shape. Now, so in order to make it more iterative, using the same operation again and again, setting using the number of, so that it will be the fractal shape, more complex fractal shape, you need to have some iterative operations, which could be a loop, or you could also use a solver. In this case, I'm going to use a loop in order to iteratively, continuously use this function for the updated shape, like this. So first of all, I'm going to name this Koch Snowflake, and I'm going to bring up the for each number loop and connect this circle and bring this Koch Snowflake inside the for loop. Then I'm gonna set it to, I'm gonna change some setup for the for each so that it will be a recursive calculation to make it a feedback loop. Make it as a feedback loop. So first of all, for the for each end node, I'm going to change this gather method into feedback each iteration, and then go to the for each begin and then change this method into fetch feedback, and this combination will become the feedback loop. Now if you go out of the loop, you'll see if the number is 10, then you'll have 10 continuous iteration in order to create a fractal, a Koch Snowflake fractal for each edge. So, and 10 might be too big. Okay, it's stuck. I guess the maximum of 6 is fine for the complexness. 10 might be too small, and yeah, it kind of stuck because it's really heavy. Okay, hopefully it will stop. I'm pressing escape key right now. Okay, I'm not sure if it's going. I might need to quit it. Okay, yeah, I think I have a problem. So I guess that's a point that you have to be careful using a fractal feedback loop, because you have a problem something like this. Okay, let me just quit it and open the file again. I'm just gonna copy paste from the final file that I've created till the part that I did. Sorry for that. Yeah, I guess it's the first time I crashed. Okay. Let me try to open the recent file. Okay. Yeah, I didn't save this. Okay. So let's just create a geometry. I just pasted the part that I did. Okay. Now I am. Okay, this part should be the same. I'm missing some parameters, so I'm going to create a null node again. And oops. Okay, so I had the parameter called size from 3 to 10. Also, let's give another parameter in order to set this number of iterations for the fractal. So starting from 0 to maximum 6 norm, just to make sure. Okay, let's set the size to 3 and fractal iteration to something like small number like 2. Copy the size and paste it into here. Paste relative reference. Then copy this fractal iteration into the value here, the iteration parameter. Okay, now this seems to work well. Now if I change this fractal iterations to 0, it's triangle. If I change it to 1, you have one triangle mountain on each edge, and for the second iterations you have another triangle mountain for each edge, which is created after the second iterations, and so on. If you increase the number, then you have a continuous fractal calculation steps, which works on each edge of the last polygon. So that seems to work well. Okay, I'm gonna go with the 5 for now. Now the 2D part of making a snowflake, the Koch Snowflake, is just it. So as you can see, it is pretty simple. Now that is not that fun though. So I'm going to use this to create a 3-dimensional vase, and that's the final goal for today. Now, first thing I would like to do, seems like the top part of this polygon is facing the normal of this polygon is facing the negative direction of the y. So let's create the reverse node to flip the normal direction just to make it pretty. Okay. And the next thing I would like to do is to create a bunch of layers of this Koch Snowflake in Y direction, and then using something like Polyloft or Scan to create a kind of a pipe shape or vase shape by connecting those sections. Right. So to do that, I'm going to use another for each loop. So bring up the for each number loop, and then connect it with this base 2D image, 2D polygon, and I'm going to set the background to black. Right. Now, first thing I would like to control is the number of layers that you want to have in Y direction, which will be the number of sections, which can be controlled here on the for each end, which is here. And since this is not a feedback loop, I am going to leave this gather method to merge each iterations. So let's add a integer parameter. Name this something like section number, and the range could be from 0 to 100. So the many layers you have, more high res you get for the final output. Let's set it to something like 40 and paste this parameter into this iteration channel. Right. Okay. Now, in order to bring this base plane on upward, I guess you have two ways to do that. One way is to use transform. Another way is to use vex. And for this purpose, I would like to use vex because for each iterations you want to know what number of iterations you're in right now in the loop to calculate the specific position for each layers. And you can do that by using transform with the expression, but I don't really like writing expression because you always have to write in one line, which is hard to see what is written there. So I'm going to use rango, point rango, to do that. It might looks harder, and might looks difficult, but the difficulties is pretty much the same compared to using transform node. It's just the difference with how you write the expression, how you write the code. Okay, so I have connected the point rango to the first input of this point rango from this for each begin. Then let's also connect this for each count to metadata to the second input, because this node contains some important information, which is the number of iterations and the current index of the iterations, the current number of the iterations on detail. If you look at it, you'll see the iteration attribute and the num iterations attribute. So the iteration is the current iteration number, and the num iteration is the total number of the iterations. So you use those two numbers to calculate the specific height of this Koch Snowflake section, as well as the scale and the rotation. And you're gonna do all those stuff inside this point rango. Let's name this transform. Right. Okay. Now, first thing you want to do is to bring up those two information iterations and the number of iterations. So first of all, iteration from the detail of the second input. Iteration int num iteration k, and from those two information I want to make some value called t, which is a float number. Goes the minimum the value will be 0 and the maximum value will be 1. So the maximum value should be this num iteration, which is a number of iterations, and the iteration is the current number. So by dividing this iteration by this num iteration, you can get a number from 0 to 1. So iteration divided by num iterations. One thing you have to be careful, this one, you have to subdivide it by 1 because iteration starts from 0. So something like this, you'll get the number from 0 to 1 based on the number of iteration. Right. So using those t, I could easily create some value for the height or rotation or the size. Okay, so in order to control the height, scale, and the rotation angle, and also maybe the wave for the final shape, let's create those parameters first. So first of all, height. And rotation angle. And what else? Scale. This could be minimum scale. And also the wave angle. I'm gonna explain one by one. Okay, I'm just gonna randomly set those numbers for now. Right, let's start with the height. Okay, so let's set the height to something like 5, and I want to make this height be the final, the overall height of this vase. So, which means that this height 5 is used only when the t is equal to 1. So other than that, you wanna so which is the highest layer's height. Other than that, it's either between 0 and 5. And you can just actually calculate that pretty easily by just multiplying this t by height, and that will be the height of the section for each section. So section height is equal to t multiplied by height, and you can update the height value, which is point y, with this section height that you have just created, right? And if you leave this loop, you'll see that each section will be placed on each section height, and the highest value, the height of this highest section is equal to 5. And if you change this height value to 3, then hole size will be reduced based on this value, right? Okay, so next let's do the rotation, shall we? So I want to use this rotation angle, and I'm gonna use this as a multiplication of pi which is 180 degrees. So I'm going to multiply this rotation angle parameter, multiply by pi, and use that as actual rotation angle. Right. Okay, and I want to have some kind of twisting rotational feeling for each layers. So this again, the rotation angle that I have set here is the final rotation angle of the highest top section. So which is same as this. You want to gradually change the rotation angle based on the number of iterations, based on the height. So section rotation is equal to t multiplied by pi multiplied by rot angle. So this is the rotation angle for each section. And to use this, I'm going to create a rotation matrix like this, starting from the ident, and then rotate matrix S rotation angle, which is this one. And then the axis for now, I'm going to set it as y-axis. It might be also interesting to change this axis for each section. To change the rotation axis, you might be able to get more interesting shape afterwards, but to make it safe, I'm going to set it as y axis for now. Right. Now I have created the rotation matrix. I'm going to multiply this point, each point with the created matrix, and as a result, I'll be able to twist the whole shape based on the set number of section, the height of the section, number of iterations. It might be hard to see, but it's actually twisting like this, right? Looks good. Now, next thing I would like to do is to, okay, let's save this just to make sure I don't get into infinite loop again. Okay, last thing I would like to do is to create a section shape. So I want to create something like a wavy shape so that it looks like a vase, which I want to create something like this kind of shape. So for the simple section shape, I'm just going to use the sine curve, sine wave, because that's the easiest way to do that. Right? And to do that, you also need to calculate. You also need to have some information with the angle in order to use the sine wave. So let's do that by creating a section wave angle by multiplying t by pi by, what was the name? Wave ang. So the variable looks pretty much the same as this one, the rotation angle, but the way to use is a bit different. So what I want to use this for is to use with this sine function, with this S wave angle that I have created. And the sine wave, if you use the sine, then the domain, the boundary of this function, meaning the minimum value and the maximum value of this sine value, will be -1 to +1. So I want to remap that value from -1 to +1 to the target value, which I want to use another parameter that I have set, which is this minimum scale. So if the sine wave's value is equal to -1, I want to set the scale of the section to be this minimum scale, equivalent to this minimum scale. If not, if the sign value is maximum value equal to 1.0, then just keep it as it is, 1.0. Something like this. And let's also create a variable, let's say scale value, sc, this. Okay, let's give more landscape here, right? Now that I have got the value here, this is also based on the number of layers, also using the wave, sine wave function. What I want to do next is to multiply the point x value with this s scale value. Also, I want to multiply the z value as well. This is sc. Now, as a result, I'll be able to get kind of a wavy, should be able to get the wavy pattern shape. Now, the angle is a bit too small right now, so let's bring this up to something like 2. And yeah, now I see some vase-like shape, and it looks good. If I increase this more, you have more like a column-like shape. Okay, so all those stuff seems to work well, so I'm going to link all those 4 parameters with this node controller. So let's bring up the parameter information, parameter interface for the node controller, and let's give those 4 parameters. And I think I heard from someone that it's also possible to link those parameters by drag and drop those value into here. Something like bring this height parameters to here by drag and drop. Now I have some errors here. I think I need to unlock something, maybe this one, forbid linking parameters from outside this output subnet, from outside this subnet. So I have checked off this option. Then let's try this again. Bring this height to here, and I think I was being able to bring this height parameter here. Now I'm not sure if it's linked. Let's set the range first and apply, accept, and see if it's really linked. Okay, it seems it is linked. Now if I change the height here, yeah, it looks like it's working. That looks good. So let's do that to promote all those parameters. So select node controller, go to the edit parameter interface. For the height, I'm going to set the maximum to 5. And then go back to the transform. For the other 3 parameters, let's drag and drop. Okay, I guess I need to uncheck this option again. Okay, so rotation angle. Let's give a space between the rotation angle. And the range, this could be 2 to 3, right? And the minimum scale, let's also give a space in between. And then for this one, yeah, 0 to 1 is fine for the range. Okay, and the wave angle. Okay, for this one, I am going to give a range from 0 to 3 again. Okay, that looks good. Oh, maybe the rotation angle I'm going to give 5 for the maximum. Okay, now let's try. So if I change rotation angle, the twistiness changes, the minimum scale controls the minimum like section scale of the vase or the column. And the wave angle changes the number of waves for the section. Okay, that looks good. That seems to work well. Okay, so finally, and let's go back to the transform node, and I want to add additional attribute to each point for this Koch Snowflake in order to use it as a color value. So if the point on the polygon is close to the center point of this Koch Snowflake, I want to give a small value for the color value, and if the point of the snowflake is far from the point, then I want to give a bit more greater value so that I can have some kind of gradational color based on the deepness, how deep it is, based on how deep it is from the outside, so that I could kind of show it as a shade, right? So in order to calculate the distance, I can use the distance function from the set 0, 0, 0, and for each section, just get the x and y value and set the y value to 0. I mean, for each point on the polygon, just get the x and z value and just set the y value to 0 so that you can always get the distance which lays on the z plane. Right, so I have just created a new attribute called distance. Now in order to use it as a color value, I want to remap into 0 to 1 because that's more easy to deal with, because right now you don't know the maximum value of the distance. So to get those, I'm going to create 2 attribute promote in order to get the maximum and minimum value of this distance attribute. So let's promote it into detail from point, then maximum, then change the new name of the attribute to max distance. Let's copy this, and for the second one, I'm going to change the minimum, then change the attribute name to minimum distance, and also check off the delete original, because you don't want to delete the distance attribute itself. Right, so last, let's create a new point Rangel to create a attribute called color. So fcol is equal to detail you just want to fit the distance attribute, which the minimum value is detail value called minimum distance, and the maximum value will be detail max distance, and set the range to 0 and 1. Okay, let's see the result. If I go to the point, you see this color value goes from 0 to 1, and so I think it goes well. Right, now leave the section, leave the loop, and what you do next is just the final touch up. So you already have those section curve or section polygon laid on top of each other. You just want to connect those to create one continuous surface, and you can do that by using something like skin sop. So bring up the skin sop and you can create a continuous lofted shape like this. Let's hide the edge, right? And I also want to normalize this just in case, and also use the facet to cusp the edges, because sometimes as you can see, this edge is smoothed out. You cannot really see the edges here. So in order to let it look like it has edge, check this cusp polygon with the low value, I guess. Okay, still not seeing it. Maybe I didn't need the normal. Right. Okay. In order to able to see a bit more clearly, I'm going to reduce the number of fractal for now and increase the number of section numbers to make it high res. Okay. Right, and let's color this using the color attribute that I have created. So bring up the, what's this, color node, and change the color type to ramp from attribute, use the col, and as a default the minimum value is set to, if the color value is 0, the black color is used, and if the color is 1, the white color is used. You can change this to try out your own color setup. Maybe I'll go with something like this, I guess. Let's also set the material color for whole display to be more bright. Okay, that looks good. Now, if you want to have a thickness for this vase, right now I don't have any thickness for this shape, but if you want to like 3D print to make something like a similar lampshade, then you need to have a kind of a thickness to this geometry. So if you want to do that, then you can add another node like poly extrude between here and create a small distance like 0.01 or something with the back option on, and you can have the front side and back side made it as whole solid geometry, which you can send it for 3D printing. Okay, and this is it. I think it was pretty simple for today. Now I did crashed my file, but the setup itself is pretty easy, as you can see. So you can change the height, you can change the number of iterations for the fractal by changing this fractal iterations to make it more complex. Make it more like a sea wave. This looks really cool. If you look from the upside, top part, yeah. And you can change the wave pattern. I guess you could create exact shape like it shows in the image right here, by changing those parameters that I have created here. If I decrease the minimum scale, and also maybe decrease some height value. Yeah, it kind of looks exactly like the 3D printed lampshade, but you have more control in order to create various kind of shape based on the system that we have created. So you'll be able to get your original lampshade based on the same system. Yeah, this is pretty interesting. And I guess the thickness is a bit too thick for this iterations. If I change this to 4, maybe that's better. Maybe you want to reduce the number of thickness for the poly extrude if you want to have more fractal iterations. Yeah, something like this. Okay, let's also add the thickness as a new parameter, and I will finish it. Set the range to 0.1. Okay, so that's pretty much it. Let me know if you have any questions. If not, I will end this tutorial for today. And the final shape, yeah, I do like the outlook of the final shape. It's just really simple to make it. Maybe it's some of you might find it too easy, but well, it's for beginners. Okay. Thank you for the comment. Okay, I don't think I need to update anything else for this. Okay, so I also had the number of side here. If I change the side here, it still works. And the section becomes a bit more interesting. If you make it more circular, the whole shape became more circular. But I guess number 3, the section number 3 is better for me. I like the number of sides to be 3. Okay, that's it. Thank you very much, and I hope to see you next week. I'm going to do another one next week with different theme. I'll try to find out something interesting for myself, and hopefully for yourself as well. Okay. Okay, I guess there's no questions, so let me end this live. Okay. One thing I would like to ask, I did implemented a thing called Skeletonize, which already exists in game dev toolkit for side FX Lav toolkit, which is called Lab Straight Skeleton 2D. Now I didn't know this existed before, so I implemented this myself in my own way. So if anyone's interested, I could also create a tutorial for this, but just for like intellectual purpose, I guess, because if you just want to use it, you can just use this node. And you can also see how it's being made if you double click on it. Right, so if anybody's interested how I approached to create that, then please give a comment. All right, I'll hope to see you next week, and I'll end this right now. Okay, goodbye.